3D internal force diagrams are very similar to 2D. We just need to draw 3 additional diagrams for Vy, Mz, and Mx. If you've mastered the 2D case, this should be a very intuitive next step. First, let's discuss how to get Vy. It is exactly the same way that we get Vz in 2D, but in the y direction. So the exact same sign convention holds, where when my force points into the coordinate system, it is negative, and if my force points against the coordinate system, it is positive. So here we see the case where F points into y, since y here has a dot, which implies it comes out of the page, which means this side. Imagine it going out of the page. The initial point has to be negative. And let's draw that. Negative F. And then nothing happens, so we have a constant load, and it jumps back up to 0. So we have minus constant minus F. Then Mz happens, and Mz is something that you have to be very careful of. I will go through the right-hand rule with you guys again, and then you will see why Mz is actually the negative integral of Qy. We know that everything has to transfer in the x direction, since the x direction is always our axial direction. If I have a force in the z direction, and we go to the x direction, the z direction's force crosses this direction and generates a moment like this, which, if you do the right-hand rule, with the y direction, is the positive moment in the y direction. Let's try the same thing with the y direction forces. If I have a force in this direction and it crosses this lever arm, the x direction, it generates a moment in this direction. Now if you do the z direction's right hand rule, you will see that your z curl is actually this direction, but our moment that the y induces is this direction. Therefore, mz is equal to negative integral of the y direction shear force. This is very, very important, and a lot of students forget this. So let's draw this now. There's no supports or anything, so I know I start at the 0 point. It's negative constant. We have Vy, which integrates to Mz. So this becomes a positive linear, very careful, positive, of minus F times the length that it crosses, L half. At L half, we have this point moment that I had to add in just for equilibrium reasons, and this point in the downwards direction. So that goes with the Z direction, which means it has to decrease my curve. Decrease by the magnitude of FL. So from plus 1/2 to minus FL half. This then increases back up to 0 linearly. This is how I get my curve. Now we will move on to torsion. A moment in the x direction is known as torsion. Torsion can only be caused by a moment in the y or z direction being transferred over to the x direction due to a change in geometry, or a direct torsional moment being applied to my bar. The torsion has absolutely nothing to do with the normal force, and please remember this. This is a very, very important point that some people get very confused about. So in early statics, we always just assume the beam to be just a bar and ignore exact cross-sectional properties, because the exact cross-sectional property could also induce a torsion. This is something we will cover later on in a future course when we cover elastostatics, for example. Let's quickly analyze how a torsion can be created. Torsion, for those unaware, is when you have a twisting motion. Imagine when you were a kid and someone would twist your arm in 2 separate directions and then it would feel really weird. That is the exact definition of torsion. So imagine this case right here. When we apply a rotational motion on one end, the clamped end has to oppose this because my bar has to be static. This opposing with this creates a torsional moment, which is exact definition when 2 x direction moments counteract each other. Imagine if we had something like this, which again is a later chapter. If I had a force being applied in this corner, F, it would induce a rotation like this across B half. So this would induce a torsional moment of F times B half. But once again, this does not concern us in the case of just simple bars. This is only when there's unique cross-sectional properties. Now I will show you a quick example of how we can have a torsion in our 3D case. Let's take a very similar example to what we did in the first case, except I'm not going to have a point moment in the Z direction in the middle. Instead, I'm going to connect it to a bar. It's connected to a 6 value support. Now in 3D, remember, this support now has 6 values, since it can both translate and rotate in every direction. So there's 6 values for the support. Let's see how our diagrams change in this case. Our Vy diagram obviously stays the exact same because nothing changed in my shear y direction. Let's quickly draw this in. I will only be drawing these 3 diagrams such that you can refer to the diagram or you can refer to the figure while I draw the diagram. There is also, for the viewer, an entire set drawn in case you want to try this yourself at home. Here we see that this has to have a minus F constant value. Let's draw the F here just so it's nice and clear. For my Mz in this case now, I will have the same thing. And for those wondering, this part will be 0 because I initially had negative y from this jump that goes into the positive y direction. So it goes in the same direction as the coordinate system. This gives me a negative jump initially. And then I have this F force that goes opposing the coordinate system such that this jumps my curve positively. So I go from minus F and I jump up to 0. This bar still has the same direction y2. So this F is actually applied to this y1. And then it transfers over to this bar. This bar has the y2 direction, same as the previous y1 direction. So this value has to be the same as the ending value of the previous bar, which was 0 after this jump. Therefore, this bar has to be 0 now. mz starts off with a value of 0, and remember, it is the negative integral of vy. Therefore, it goes linearly increasing, once again, to fl. Just a little recap. And now what happens to the mx curve? So mx curve obviously starts off with 0. We have nothing that could possibly influence the torsion on this bar. However, there's not 0 torsion here. So if we think about it intuitively, if I'm at this point, my bar does have a tendency to rotate like this because this force crosses this distance. So intuitively, I should have some sort of torsion. How does this torsion get generated in a meaningful way such that we can solve it in the diagrams? We look at the local coordinate system transfer exact same way we did in the previous lecture. So here we see that the x2 direction is downwards now, which was the previous z1 direction. So because of this, we know that x2 is equal to z1, primarily in the final point. So if you guys remember, if we had a moment that's initially downwards with a double arrow, like this, it transfers exactly like that here. But this direction change, the force can't randomly change its direction. That wouldn't make any sense. But what we define that direction as does change in this beam because the axial direction always has to be x. So now this z moment has to be transferred to the x direction, and it transfers directly because the sign doesn't flip, the x direction is not pointing upwards. Therefore, this part has to have a torsional moment of positive f times l. And this completely makes sense from what our intuition said, because I told you that we have a torsional moment caused by this one crossing this direction. F crossing L gave us this torsional moment, which is exactly the magnitude of the torsion we have. If you want the full uncut version of every lecture right away, they're already available on my website with the link in the description. The lectures cover all the topics on screen right now. If you found this video useful, please like and subscribe to help the video reach more people trying to learn mechanics. Everything I produce here is done completely from scratch, so these videos take a really long time to make. Thank you.